consider for a moment your favorite technology. It might be a camera, it might be your favorite app. Where did it come from? What made that technology? And I can tell you the answer for every single person in this room. The answer is biology. Because every single technology and invention that we've ever made has, by default, come from the human brain, a biological computer. So this idea of when we look at developing technology and developing into our world, the reality is we have to go back and look at how biology has brought us to this point. Humans have been developing technologies, frankly, for longer than we've been Homo sapiens. And through that, we've made our lives easier. We've made our lives more productive. We've enabled the ability to support over 7 billion people on this planet, maybe not sustainably. But we've been able to create all of this. And in what context? You see, there we go. At the end of the day, the globe is the circular economy, right? And this isn't shocking. The idea of a circular economy often references back to biology. And the reason why I want to make this point is because when we think about everything that we've done, we tend to think about it very linearly. And in recent years, our technology has been developed with a very linear thought process and approach. But what's actually gotten us to this place was through the principles of a circular economy. In the circular economy, this is a very helpful diagram, right? But it's really taking the idea of trying to translate our current linear economy-based systems into a more circular economy-based system. How do we take what we're currently doing and make it look more like biology? The reason why it's so important to think about it in this way is because when you're operating within a circular economy, the moment that you pull out a resource and fail to reuse it effectively, you set up your system for collapse. And a new system can come in and rebuild, and we've seen that happen across evolution, right? We know that when the dinosaurs died off, it allowed mammals to become the dominant creatures. But right now, we're developing our technology in a way that's very linear. We have a really big resource sequestration problem. And obviously, this is dramatic, but only up to a point. You see, even as we talk about trying to make these current technologies more recyclable, they fundamentally aren't. They fundamentally are not the best systems to recycle with. But biology has been doing this for how long? Certainly longer than humans have been inventing. So, almost 2 years ago, I was at a networking event where I met the gentleman on the screen here, Asha Gabi. He's the founder and CEO of my company, Conaku Inc. And that first time that I met him, he began telling me about Conaku and what Conaku is doing, which, to be honest, is pretty cool stuff. I think I let him go 3 sentences before I interrupted him with questions, but that probably speaks to my impatience. But I got something really powerful out of that conversation with Ash. 2 things, actually. The first thing is that he is someone that truly understands the power of biology. He understands that biology itself is a technology. This is not something that is completely isolated. I think more people are starting to appreciate this fact. But it's also something that maybe most people don't know how to act on. This idea of using biology as a fundamental technology has existed within academic circles for at least decades. But I'd never actually seen a commercial way to get there. Some things are best developed through business, and I really think that this is one of them. And so Ash has built Conaku around the fundamental rallying cry that bio is tech, that this is a different way to look at biotechnology. See, traditional biotechnology will tell you that you develop a technology to fix biology. That's what our pharmaceutical industry does. And this is really powerful, but it misses a really powerful point, which is that the biology itself has solved many things that we have yet to be able to do. Right? For example, we've got a couple of evolved systems here. Now, each animal, I'm really glad Peter gave a really great description of this. So he had a circle talking about the sensing, the thinking, and the acting. And that's exactly what we are so good at doing as humans, as canines. Our sensory systems are, quite frankly, phenomenal. As he mentioned, the human brain is 1/3 dedicated to vision, and our visual recognition still far exceeds what we're able to do with AI. And a dog has an ability to smell that's so powerful that we, frankly, raise and train dogs specifically for this purpose. And so some of the technologies that we have, such as moving around, we've developed transport pretty well. We've been able to develop visual and auditory systems pretty well. We haven't been able to develop smell, or we wouldn't still be using dogs in airports. So why is this? When you look at vision, or color more specifically, it came down to the discovery of the RGB code, red, green, blue. The reason that's the code is because there are 3 receptors in your eye, or 3 types of receptors for color. They detect red, green, and blue. And with just those 3 receptors, you're able to see this entire color spectrum. Apologies to the males in the room that don't see all of the same colors. You're missing out. But this ability to develop this technology has had an incredible value. But what about things that we haven't done so well, right? We haven't mastered smell, as I mentioned. What have we done to try to overcome that? It's not that we've ignored the issue. In the food industry, you'll put together a human taste panel. You do this to try to balance out variability from person to person, varying degrees of success. We've used animals, right? I mentioned, of course, canines. They're the ones that we think of most, but there's companies that have developed rodents for various purposes. Birds, bats, you name it, we've used them. Dolphins. Even the military has explored some of these things in some very creative ways. And of course, we've used silicon technologies a lot, especially in the last 100 years, to try to solve these problems. And we keep turning to silicon for the solution because silicon has continued to provide solutions for us so reliably. I think that we just finished seeing an incredible set of examples of what these hardware-based technologies are capable of. And they empower people in a really powerful way. But we're still missing pieces. So why is it that in the case of smell, we haven't solved it? Sorry, I'll have to go back, yeah. And the reason is that smell is actually a lot more complicated than vision. Instead of 3 receptors, a human has 400, a dog has 1,000, and an elephant has 2,000. And so the same way that just those 3 can create this full visual spectrum, these 400 allow humans to distinguish over 1 trillion smells. And the reason that you didn't know that and that that isn't intuitive is because 1/3 of your brain is dedicated to vision. You don't think about it. And the other problem is we communicate with words. But for the 1 trillion smells, a college-educated English speaker has about 80,000 words. That's a really big gap. And as I mentioned, these are things that I believe are best developed commercially. So if we go back to the example of vision, if I can. With vision and sound alone, we've created an industry that's over $2 trillion per year. And we didn't realize that value right away. It took over a decade for color TVs to be on the market before they even reached 50%. Because until someone saw it in person and realized that difference, they couldn't understand the value. And what is then the market application for smell? It's huge. I'll start with the easy examples of what we already use dogs and animals to do. Security. Healthcare. Healthcare is actually interesting because it's not just dogs that we've been able to find. Of course, dogs can smell cancer. They can see a seizure before it occurs. They can detect an acute event for a diabetic patient. But there's also a woman in the UK who can smell Parkinson's disease. And she can actually do it so well that when they did the study to validate her ability to actually diagnose, she found Parkinson's in someone that they thought didn't have it, and found out within a year that they did. But then I also mentioned the food industry. How are we currently developing and marketing tastes? Human taste panels. That doesn't really tell you how something's going to perform, and how do you get the information that you don't know the words to ask for? One of the things that's made AI so powerful and so able to help humans is because it finds connections that we don't find. This is the idea behind using these machine learning algorithms. Let it find associations and drive it. That's an opportunity that we're missing. When we look at agriculture, there's a lot of information you can get from visual systems about plants, of course. But what about when you have things that are very, very small? It gets a lot harder. But for example, there's currently a beetle infestation in Kruger National Park that they are now training dogs to be able to smell. Because when the bugs have saturated the plant, they produce a compound to tell the other bugs to stay away. It's already been used. So smell has all of these incredible potential applications, and we just aren't looking at it. But we should. Which means that we have a fundamental question, which is whether we can make this into a technology. And we ask, is it a technology or can it be made into a technology? But what the real question of this is can it be engineered? So what's the difference? Okay, science, we research, we study things, we learn things, that's great. Most modern technology is in fact applied science. So it's the ability to use what we have learned about these systems and to control and manipulate them for an outcome of our desire. So the question is, can I engineer biology to make it smell for me? Oh, just wait. Now, in order to do this, you have to have a language for it, right? So an architect, they draw blueprints. And from those blueprints, you get a house. If you're doing software, you're going to have a programming language. And with that, you're going to build your program and your application. And biology has a coding language too. It's DNA. And in the incredible advancements and understanding of biology in the last century, one of the things that we've discovered is this genetic code, and it's how to use this genetic code. So if I'm telling you that this is a code, and this is a language, then it suggests that I should be able to insert an instruction to create the output that I want. That's engineering, right? So, quick aside. A few decades ago, some biologists studying in the ocean waters, I believe near Hawaii, but I could be wrong, there's a jellyfish that fluoresces. It's very pretty. And they were able to isolate the DNA that makes that fluorescent protein. And it's now called green fluorescent protein. What if I take that piece of code and put it into a cell? Do I get a fluorescent cell? Yeah, I do. And so this is an example of a very simple program, right? I've put in an instruction for a single output. So then you start to ask, can I make this more complicated? Can I make this conditional? This is a diagram showing the physiological olfactory signaling pathway. So this is the pathway by which, let's say, some vanilla is floating in the air, you inhale. This is going to be the pathway that occurs inside your cell that results in an electrical signal going to your brain. I don't have to use this exact pathway because I'm a synthetic biologist, because Konaku does synthetic biology. So what if instead of just saying I want fluorescence, I want it to only fluoresce when there's an explosive there? Can I do that? This technology is in a device in our labs right now. This device is a fundamentally new device because it is not hardware, it is not just software, it is also wetware. This is a device that has living biological cells at its core. The fundamental technology is to have living cells that have been engineered to detect what we program them to detect. I've used the example of explosives here, but we can detect any of it. And by using this kind of system, we are now harnessing not just the benefits of biology, but we're leveraging the benefits of traditional hardware technologies in a way that we've been missing out on. It's very great and good to have a dog that sits down when it smells an explosive. What explosive did it detect? What if the handler's in on it? What if instead, when that detection event occurs, it occurs in a way that I know what was detected, that I can alert the handler immediately nearby, that I can send that to a central security response area? It's a different technology. And you can imagine this for a lot of other applications. Perhaps I brew beer, and it doesn't have an infinite shelf life. As it gets shipped to different parts of the globe, the temperature gets maintained better or worse, depending. How do I know that that product actually tastes the same everywhere that it goes? How do I know that my customer that loves my product is actually getting the same product every time? Because without a reliable product, you're not going to have very reliable customers either. So this is something that I feel very powerfully about because it represents so much in terms of what technology is fundamentally. It represents so much about what technology needs to be, which is more sustainable. And it represents so much about moving forward in a way that says we have developed incredible things. Now it's time to make it better, and now it's time to let our technologies leverage each other. This is the first step. So, as included in the introduction, there is the idea that it's not just about creating sensing machines, so that's a really important start. When we look at computers, there are things that computers do far better than humans. And there are things that humans far outpace computers for. Some of that will change over time as we develop computers, silicon computers, to do things differently, to do things better. But some things come out of the fundamental. We cannot ignore the fact that biological systems are more energy efficient. It was mentioned in the previous talk that it takes 6 watts to run the entire visual system of your brain. But it takes 6 watts just to stream a video on your smartphone. And at the end of the day, energy is the ultimate currency that we're going to be facing. So to us, we view sensing as the first step. Sensing is a great tool for developing these interfaces. Right now, we have a device that has a biological core, and it has hardware, and they have to be able to communicate with each other. And that communication then has to be developed in the other way around, to control. And as you develop those interfacing systems, and as you have a true bidirectional information flow, then you can start looking at harnessing the remaining power of biology, the part of biology that has created all of our other technology. And that's the ability to do computational biology. And so this is why bio is tech is our rallying cry. Because it doesn't matter what aspect you look at, biology is technology.